these chapters, we discuss about the design of reinforced concrete staircase. You know that the design of the staircase is very similar to the slab. You will see a lot of equations to be quite identical to those being used for the design of the slab. Only that there are certain parts of the analysis which varies from the slabs. In these chapters, we have introduced the components of the staircase, where there are regions of the flights and there are also landings. We also introduce you the terms of the riser and goings. And due to the existence of these steps, when we need to estimate the weight of the staircase, some conversions will be required, where we need to estimate the average thickness of the staircase on basis of the y here. The y is calculated from the formula here, as computed from the trigonometry relationships. The average thickness here, it will be defined by the y plus half height of the riser, and then the self-weight will be calculated by multiplying with the unit weight of the concrete. This self-weight is later to be added up with the GK, and then the total GK will produce. In order for you to determine the design loads, you're going to multiply the total GK with the factor of safety 1.35, and for the QK 1.5 for the ultimate limit state. With that, we are able to determine the UDL acting along the staircase. From the examples that we have discussed in these chapters, we see quite a variety in terms of the design of the staircase. Due to the setup of the staircase, the calculations vary slightly, especially when you need to estimate the loads, particularly in terms of the moment acting on the staircase, as well as the setup conditions that you consider when you need to calculate for the deflections L per D ratio. Specifically, we are talking about calculating the K, which is to be adopted into the equations here. If you see the first example that we have discussed previously, by looking at the locations of the beam, we are able to determine the effective span of the staircase. By looking at the existence of the adjacent slab, we know that whether the staircase here, whether it is intermediate span, end span, or a simply supported span, which in this case, you have adjacent slab in front and behind the staircase. That means this staircase, it will be considered as an intermediate span. Having it as an intermediate span, the bending moment diagram will look something like this. There will be moment at the midspan and also moment at the support. And the bending moment will be determined by WL square per 10. But when you come to the second example here, you have span adjacent to a slab. However, this side you have no adjacent slab. Now you know that the staircase span here is an end span. One side is adjacent to the slab, another side is not. This will give you the bending moment diagram, something like this. The end span here, you have no moment. There will be moment at somewhere at the midspan of the staircase, and there will be moment at the support of the interior support. You can use the formula FL per 10 to calculate that. You need to also be careful with the UDL. The UDL of the landings is normally not the same as the UDL at the flights. It is specifically due to the self-weight of the steps of the staircase, where you need to consider an average thickness of the staircase. However, when you're talking about the landing, the thickness, it will be as given in the diagram. Now when you come to the third example here, you don't have any adjacent slab beside the staircase. Now the entire staircase here will be considered as simply supported span. This will lead to the bending moment diagram, something like this. And the moment, it will be WL square per 8 or FL per 8, which is different from the continuous member, assuming it to be FL per 10. What I want to emphasize here is that you have to look into the setup of the staircase for you to decide whether it is a continuous span or whether it is a simply supported span. If it is continuous span, you will need to decide whether it is an interior member or it is an end member. The bending moment diagram will change accordingly. Not only that, the K that you use to calculate the deflections will vary as well due to the conditions of the span, whether it is simply supported, whether it is an end span, or whether it is a interior span. Now that you have designed for the main reinforcement bar on basis of the ultimate limit state, the secondary reinforcement bar, you know that it is not meant to resist the bending moment, as the staircase is designed to withstand the load in the one span direction. The bending moment will occur in these directions, but not in the transverse directions. With that, you only need to provide 20% of the amount of reinforcement bar from the main reinforcement bar as the secondary reinforcement bar. Its main purpose is to control cracking, as well as to provide mechanism for the main reinforcement bar to be tied together so that it remains in the intended locations during the casting. You need to check for the shear resistance. And this shear resistance, the principles is similar to the slab. Basically, the same series of equations that you use are similar to the slab. For the moment, actually is also similar to the slab. And you need to check also for the serviceability conditions. This will include the maximum and minimum reinforcement bar, the maximum spacing of the reinforcement bar, and normally the thickness of the staircase are less than 200 mm. Therefore, the equations used, it will be also identical to the slab. And you need to check for the deflections. We mentioned that normally staircases do not require compression reinforcement bar. That means there are chances that the L per D ratios is going to be using the first equation here. However, there is no guarantee that it always falls here. So what you can do, you will need to first calculate the rho and the rho note based on the equation here, and to decide if the rho is less than rho note, these equations will apply. If the rho is more than rho note, you will use this equation. And then the calculations L per D limits will be multiplied with the modification factors. Based on the three examples that we have done, this is the second example, and this is the third example. If you observe the calculation steps, we found that the shear resistance are normally easy to pass, and normally we are able to provide sufficient reinforcement bar to pass for the moment resistance. However, there are high chance for the deflections fail for the staircase. This can be one of the major concerns for the staircase. If you encounter the staircase fail in L per D ratio, you can actually increase the amount of reinforcement bar, as this will increase the modification factors so that you have better allowance for you to pass for the L per D ratio limit. However, if you test the value, with the maximum ratio of 1.5. When your L per D ratio limit is still less than the actual L per D ratio, that means the provided effective depth of the staircase, it will be insufficient. Most likely you will need to redesign the staircase so that it passes. There is another ways for you to increase the chances of passing, where you might need to increase the grade of the concrete. But I believe the contributions, it will not be that significant. The most effective way to pass the deflections, it would be by increasing the thickness of the staircase. With that, this concludes the entire chapters for the design of the staircase.